Very good morning to all of you. Already we started our unit number 3 in the previous sessions of before today. Today is the lecture number 27, subject to fluid mechanics, 11/2021. Okay, so we are learning about the dimensional analysis. Already we have seen many things in that we started in from the lecture number 25 that 2 November in dimensional analysis and model analysis we need a basics units, that is length, mass and time, and why we are going for the analysis. We have discussed the solution to several engineering problems, the testing of the dimensional homogeneity of equation of motion, of fluid motion, deriving the equation expressed in terms of non-dimensional parameters to show the relative significance of each parameters, learning model test, and presenting experimental result in systematic manner in terms of non-dimensional parameters, thus making it possible to analyze the complete fluid flow phenomena. And we have also seen the dimensional homogeneity. What is the dimensional homogeneity? For the mathematical equation governing relationship between the variables in physical phenomena is homogeneous if the left-hand side of equation and right-hand side of equation balance dimension. If you see this equation we have seen that the discharge equation of orifice. In that case, if the dimension of left hand side and right hand side matches, then we will say that the equation is dimensional homogeneous. The Q is nothing but discharge. As discharge, we are measuring area into velocity. Area we are measuring in length into length, that is length into breadth. Both our dimensions are length. So length into length, that is L square, and the velocity we are measuring length upon time, that is meter per second. Okay. So we know that there are three basic dimensions. That are nothing but mass. We are denoting it m, length we are denoting with L. This is the dimensional, and time we are denoting by T in terms of dimension. In terms of unit, we are denoting as the gram or kg, kilogram. Length we are measuring in meter or centimeter, and time we are measuring in second. Okay, so these are nothing but the units, and these are the dimensions. So generally, the dimension analysis is very important for understanding the fluid flow problem and non-dimensional parameter also in the fluid flow. Okay, so I think so that this is visible. And also we have seen the non-dimensional equation, that is Lass's formula for the weighted parameter. P is equal to 2.67 of Q. In this you can see the weighted parameter is nothing but the perimeter. Perimeter dimension is L. We are measuring in the meter. And right hand side is where we find under root of Q, that is discharge, having dimension under root of L cubed by T. You can see in this equation the left hand side and right side they are not matching. That's why this equation of Lass's weighted parameter is dimensionless, not homogeneous. That is we have seen, and also we have given to find out this homogeneity of this equation mu is equal to 1 down to 2gh, so you can do that. Then for dimensional analysis, there is two types of method we have already discussed in the previous classes. The video lecture is available. There is relay method and the nothing of pi method. So, so relay method is a function of x, y, and z, and then we have to find out the multiple equation. If three unknown and three equations are there, then we can easily find out. But if we have more than three unknowns, then it is very difficult to find out this equation. To find out the now, in next class we have seen the working of pi theorem. The pi theorem states that if there are n number of fundamental dimensions, there is n and t involved. This length, mass, and time, these are the basic dimensions involved in the phenomena. Involved in the phenomena controlled by n number of variables, then the phenomena can be described by n minus m independent dimensional groups known as pi terms. So if there is number of variables and there are basic variables, so that m, so n minus m is the independent dimensional group, and that example, if there are in equation there are we have solved there one example also in that different sorry, you can see here the discharge is a function of high H, G, L, Z, rho, and mu. Mu is the viscosity, rho is the mass density, Z is the energy head, L is the end, G is the gravitational acceleration, which is the hydraulic head. Okay. So n number of variables are 7. We have basic variables 3. So 7 minus 3, then we required 4, 5. That is the Buckingham's pi theorem, and we have solved one example also using that theorem in phi 1, phi 2, and phi 3, phi 4. These terms we are find out by the dimensional analysis. Okay, the discharge equations. Okay, then now we will see uh, uh, different types of the dimensional similarity or dimensional analysis. So basic dimensions, we know that there is nothing but the mass, length, and time. Based on that, we can draw the multiple dimensions, and you can see one by one. We, in this slide, this page is taken from the Dr. P.N. Modi and Dr. S.M. Seth book. So we can refer that also, and also some NPTEL slides are also available on internet. And the Froude book is also there for the fluid mechanics, and R.K. Bansal books are there. Mainly R.K. Bansal book is for the mechanical engineering student. Okay, so I think so. This previous what we have covered in the unit number 3 or discussed with you. Now we'll proceed today. So we'll see one by one in the dimensional analysis, the geometric, kinematic, and dynamic similarity. So I will go with this the quantities. In the first column, you can see here. In the first column, where the quantities are given. Okay, these are the quantities. Okay, then the symbols for that quantities. And dimension in terms of mass, that is mass, length, and time. And FLT means the force, length, and time. Okay, so here you can show that dimension is divided into two types, that is with mass and with force. Okay, so you can see here one by one, and then SI unit of that dimension, metric unit of that dimension, and the English unit of that dimension is given. So we know that length is nothing but is mentioned or symbol is capital L or small l. If you say the dimension is the capital L for the length, here also in the force system it is L, and SI unit of length is we are using mostly in meter, in metric unit also in meter, but in English unit that is foot on second we are saying it is measured in the foot. Then area is nothing but symbol A, and area is nothing but length into breadth. You are generally seeing that, but we are measuring both length in case of breadth cover. So that's why the dimension of the area is L square, and in case of force system also L square, and the SI unit of area is meter square. All these things you know, but I'm revising. The volume is nothing but the three dimensions, that is length into length into length. That is length, breadth, and height. So in general, we are saying that length, breadth, and height. But all these dimension, length we are measuring the length, dimension breadth we are measuring length, and height is also we are measuring the length or height of it. So length that is L cube, and for positive also there, but in SI unit and in metric unit we are using meter cube, and in English unit we are measuring in the cubic feet. Similarly, curvature C is 1 upon L, 1 upon L, that is a slope, that is per meter or per foot in a phase system. Slope S or I, we are relating M0, L0, T0, or F0, L0, T0. The slope is nothing but difference of the 2 points, both are in meter per meter. You can say it is dimensionless, feet per feet in a PS system. Angle we generally measure in alpha or theta, generally theta. It is also M0, L0, T0, or you can say radian or degree. We are measuring the similar the shape factor, neta or eta, you can say. You can measure M0, L0, T0, M0, L0, T0. That is the dimension level. Okay, so that we are measuring for the geometrical properties of the dimensions. So the quantities are length, area, volume, curvature, slope. These are the geometrical quantities, and then we'll go for the kinematic quantity. What is the kinematic? You know that in kinematic of fluid flow, the force is not considered for the flow, and uh, in dynamic, we are considering the force was in flow. So here you can see the quantities is nothing but again the time, generally symbol t or small t, and dimension of that is t, capital T, SI unit is second, metric unit is second, and uh, English unit is also second. Similarly, velocity we know velocity is nothing but meter per second. To write down velocity the meter per second. If you write down the dimension, it is length upon time. Okay, time generally we are measuring in the meter, and sorry in second, and length we are measuring in meter. So meter per second is the velocity. Similarly, if you go for the acceleration, acceleration is nothing but uh, meter per second square, meter per second square. So if you write down, so the dimension of the this is you know, meter per second square. To write down, so L upon T square. Okay, so acceleration we generally measure. Angular velocity omega is also 1 upon T, radian per second is unit. Frequency is divided by eta, that is 1 upon t, that is also uh, per second we are measuring the frequency. Acceleration, linear acceleration is length upon time square. Angular acceleration is also 1 upon t square. Gravitational acceleration G also we are measuring in meter per second square. So dimensional quantity L upon T square. And discharge we are measuring meter cube per second. That is area into velocity. L cube by T. It is the dimension of the discharge. And discharge per unit width, that is Q L square per T. Yeah? Because per unit width we are measuring, so here 1 L will cancel, and that is meter cube per second. Per meter is the uh, unit of the discharge per unit width. Generally for the spillways etc. we are measuring flow over. And then kinematic viscosity mu is nothing but L square upon T, area upon time. You can see the viscosity is meter square per second. Okay, and circulation is nothing but is also as L square upon T, and it is also measured in meter square per second. Also, we will see some of the dynamic this I've taken from the PM book. So you can see the dynamic units are or dimensional units are mass, mass. You are generally denoted by symbol m, and it is measured in the MLT system, that is M, and if you force system, if you go for that, Ft square by L. Okay, Ft square by L. So we know that the force is nothing but mass into acceleration. Okay, in terms of force, if you write down the mass is equal to F upon A. F is nothing but this force, Newton, and if A is the acceleration is the uh, meter per second is be below, and T will come up. So if you write down this, it will be like this. So F upon A square. So this T will square will come up. So that's why Ft square upon L. Okay, it is mass. Generally, we are measuring SI system in kilogram. Force F we are measuring in Newton. So if you write down in MLT system, this MLT square, that is mass into acceleration. In F4 system, it is F, and these are in SI unit Newton. In KS system, it is metric system like KGF, and in the football second, it is denoted by pound M. Okay. Similarly, weight is nothing but acting the gravitational acceleration with the mass, mass into g. So weight generally is nothing but the force, that is mass into gravitational acceleration here. The unit or dimension is same as the force. Okay. Similarly, mass density rho, we are generally measuring meter cube, meter upon L cube, and mass upon L cube, mass upon L cube, that is mass upon volume, mass upon volume, mass upon volume, that is cube, that is denoted by rho. Write down in the FT system, it is mass, the mass system, mass is nothing but T square upon L. So we have to write down mass and volume. So Ft square upon L cube, because L into L cube is L raised to 4. So that's the unit of this mass density kg per meter cube. Kg per meter cube. Make a correction. Okay, or gram per centimeter cube. Okay, so that can be written like that also. Similarly, the specific weight omega and specific gravity s, Similarly, for pressure, we are measuring Newton per meter. You can find out the dimension for the dimensional unit is mass upon L square or F upon L square, that is pressure, Newton per meter square. Similarly, shear stress is also measured in Newton per meter square. The dimension is same. Dynamic viscosity mu is m upon Lt. Okay, that is tau upon change in velocity. So you know the mu is nothing but tau is nothing but mu in times so u by rho I. So to write on mu is tau upon rho u by rho I. Okay, so you can easily find out the dimension for this. Uh, Tau we are measuring in area, okay, and change in velocity so that you can, if you explore, then you get this ns Newton second per meter square. It is the dynamic viscosity, okay, and then sigma is the surface tension, okay, surface tension F upon L or M upon E square. Similarly, modulus of elasticity E and compressibility is 1 upon modulus of elasticity. So this is also Newton per meter square Pascal, and compressibility is meter square per Newton, that is inverse of modulus of elasticity. So that these are the some dimensional units that we are uh, we need for the study of the dimensional uses and for the study of fluid flow problems. Okay, so we have seen these basic dimensions and the some of the terms we need. So if you say that dimensionless proves in fluid dynamics, in fluid dynamics, 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 generally, yes, generally, uh, there are there are 8 variables, 8 variables, eight there are 8 variables to define to define to define fluid fluid flow fluid flow phenomena phenomena. Okay, so it may be they are first pressure uh, pressure denoted by P, pressure P, length denoted by L, the viscosity denoted by mu, and surface tension denoted by sigma, also speed of sound, speed of sound denoted by alpha, acceleration due to gravity due to gravity, that is G, and density, mass density, you can say density generally are interpreted as rho, and velocity, velocity generally we are interpreted as p. So these uh, to define the fluid flow problem, these units we may need. These are for to define the fluid flow problem. In this, you can say that in this you can say the basic dimensions, the basic dimensions are required to describe required to describe required to describe about eight about eight variables about eight variables. So 8 minus 3 is equal to 5. So, so if you reckon the 5 terms, 5 independent independent dimensionless groups can be formed. So in previous example we solved the four-dimensional group we have found because seven independent variables are there, seven variables are there, and 7 minus 3 is 4. So in previous example we solved in previous lecture there are 4, but in more example, if 8 variables are required to describe the fluid flow problem, then 8 minus 3, 3 are the basic dimension, then 5 independent dimensional group can be formed with with these variables. With these variables. Okay. Now we'll see the important dimensional less numbers. Okay. So in dimensional analysis problem, uh, already we have this problem on backing the diagram we are doing, and we have find out the four independent dimensional variables. Okay, if you see this phi 4, phi 3, okay, all these are nothing but dimensionless numbers. L1 LH, no dimension. Okay, here Q is discharge. To find this dimension, phi 1, that is dimensionless. Phi 1, phi 2, phi 3. In previous example, we have solved this example. Is given by the discharge is equal to function of H, G, L, Z, rho and mu. So that we have find out total Q, H, G, L, Z, rho, mu. How many? 1, 2, 3, 4, 5, 6, and 7 variables are there. So basic dimensions M are 3. So N is 7. 7 minus 3 is nothing but 4 pi terms are there. This example already we have solved earlier. No need of going for further. So you can refer that from the Google Classroom, and you can okay, you can understand. So these are the some of the dimensional similarities we have discussed today till now. Okay, that are geometrical, that are kinematic, and dynamic. Okay, these all similarities you will find in different books also. You can understand how to find out the dimension and units, as per the metric, as per the foot per second, and as per the SI units. Okay, so here lots of terms are there, and also some dimensionless numbers are also given in this table. That is Reynolds number, Froude number, Euler number, Weber number, Mach number, friction factor, kinetic energy correction factor, momentum correction factor, and efficiency. Okay, so all these are the dimensionless numbers. You can see here no units are there because these are nothing but the dimensionless numbers. Okay, so one by one we will see the each numbers. So if we go for that, uh, so first we'll see the Reynolds number. First we will see the Reynolds number. I will write down the dimension dimensionless, dimensionless numbers, dimensionless numbers. Okay, in that first we will see the Reynolds, Reynolds number. Reynolds number generally it is denoted by R, and it is nothing but R is nothing but it is the ratio of inertia force. It is a ratio of inertia force upon viscous force, viscous force, inertia force upon viscous force. So in short, you can write out IF upon VF. Okay, inertia force upon viscous force is nothing but Reynolds number. So we know that IF is nothing but inertia force is nothing but inertia is nothing but mass. Inertia force is nothing but mass into acceleration. Mass into acceleration. So mass generally in dimension we are denoted by m, capital M, and acceleration dimension L upon t square. Okay. Okay, and we know that mass is nothing but we know that density, mass density, that is rho is nothing but mass upon mass upon volume, mass upon volume, and we know that mass is nothing but we are measuring in the kg per cubic meter. Okay, so if you write down in terms of mass, mass is nothing but rho into volume, rho into volume. Okay, rho is nothing but density. Rho is nothing but your density. So to write down this in the above term, IF is equal to inertia force equal to mass into volume. Rho volume generally we are in dimension it is written as L cube. So rho L cube into acceleration is L upon t square. L upon t square. Okay. So if I will write down this, so if you further I will write down rho into L square into L square upon t square. So we know that velocity v is equal to L upon t. If you write down v square is nothing but L square upon t square. Okay. So if I write down the inertia force now it is equal to rho L square into v square. Got it? So inertia force is nothing but rho into L square into v square. समझ में आया ये कैसे आया? So that is very simple. So this is now our inertia force. It is now our inertia force. Okay? And the is nothing but viscous force, viscous force, VF, nothing but shear stress, shear stress into area, into area. Simply we know that shear stress we are generally denoted by tau into L square. And we know that tau is nothing but shear stress Tau is nothing but shear stress, which is equal to take Samir. Just who is joined? Too late, beta. Okay. So shear stress, we know, is nothing but mu into what is it? Mu into dou u by dou y. Okay. Dou u by dou y. Dou u is the change in velocity and with respect to change in length. Okay. Change in velocity with respect to change in. So we know that viscous force Vf is equal to mu into change in velocity, that is velocity is nothing but you are measuring L upon T, change in length into dimension, if you write down that is but L so into square. That is area. Area is L square. Okay, this L square is for area. Okay, this velocity. So this L will be cancelled. So Vf viscous force will be in terms of dimension. You can write on mu L square T raised to minus 1 because upon T. Okay. Now, what is the Reynolds number? Reynolds number is nothing but inertia force upon viscous force. So write down inertia force is rho L square V square we find out above upon viscous force is mu L square T raised to minus 1. So T raised to minus 1 it will come up, it will be T. So Reynolds number R is nothing but rho upon this L hmm? So it will be rho square L square V square upon, if you divide and multiply here this, if you separate it, mu into L into L by T. So this T will be here. So this L by T, you know, V is nothing but L upon T. So will be R is equal to rho, this L and this L will be cancelled. So it will be, this L will cancel. So L, this is V is equal to V. So V, this V and this V will be cancelled. Rho LV and upon mu. This is nothing but the dimensionless number, and it is called as Reynolds number. Reynolds, Reynolds number. This is called as Reynolds number. Inertia force upon viscous force is nothing but Reynolds number. So if you can write down the significance of R, that is Reynolds number, is Reynolds number is Reynolds number is number is Reynolds number is prominent 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 in pipe flow problem. Pipe flow problem. Okay, this is the significance of the viscous force is this viscous force is tau. Okay, so this is nothing but Reynolds number. This who is the full body is joining and doing the what is the right? So normally you are running the lecture on time. Okay, so this is nothing but your Reynolds. Okay, now we'll see the next dimensional number. Second is nothing but Froude number. Froude number. This is the name of scientist. Okay, so you can see the spelling of Froude number. It is generally denoted by F. Froude number it is denoted by F. Okay, it is nothing but under root of ratio of inertia force to the gravitational force. Okay, so you know that IF is the inertia force, and GF is the gravity force. Okay, this you know. IF already we have calculated in previous. Is nothing but mass into acceleration. Mass we have written in terms of rho into L cube. Acceleration we are writing to L upon T square, where V square is equal to L square upon T square. So IF is rho L square V square. Okay. Now the gravitational force GF is equal to mass into gravity. G, that is the gravitational acceleration. G is the gravitational acceleration. So mass again you can write down rho into L cube into G. Okay. So F is equal to under root of IF is rho L square V square upon rho L cube into G. So here you can see that F is equal to under root of rho will be cancelled, V square upon L into G will remain. So V will taken out, V upon under root of LG is nothing but Froude number. Or if you, in terms of head, if you write down to V upon under root of YG or GY. Okay, where 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 y is equal to depth of flow depth of flow in channel depth of flow channel. Okay, so this is the Froude number. This is nothing but the Froude number. The significance of Froude numbers is significance significance of f Froude number in channel flow gravity force gravity force is prominent or dominant, whatever you can say, prominent, and therefore, therefore, fraud number, fraud number, therefore, fraud number, in therefore, fraud number is a ruling number, ruling number, ruling number in channel channel flow problem. Channel flow problem. Okay, so this you know that these are the two numbers. Okay, so today we are seeing the basic dimensions and dimensional analysis of the geometrical similarities, then kinematic similarities we are seeing, and we are seeing the dynamic similarities. Okay, and also today we are seeing uh, small number and broad number, which is denoted by R, which is denoted by F, and you know that R is nothing but inertia force upon viscous force, and in broad number it is under root of inertia force upon gravity. Okay, and then we have derived the equation for the two numbers, dimensionless number, that is log number and velocity. We will see tomorrow the Mach number, the Weber number, the Euler numbers, and then we will see the model laws. We will see the model laws in tomorrow class. Tomorrow class will be during the practical hours. So I will request all the students they should join the class tomorrow also on the practical. Okay. Thank you for joining, and I will share this video also with you. You are another class. We will continue the online classes till any notice for the physical. Thank you. Any question? Any questions? Question is Muhammad Abdullah Bulgari, Samir, 1% will be okay, I request all your colleagues to ask them to join the classes. To talk to them.